All right, so now we are going to take a look at solving the other part of our differential equation from our separation of variables method. Okay, so here is the theta part of our partial differential equation from before. Remember, we said that part of our equation was going to be equal to the constant m squared, and beta we said was equal to our constants 2ie over h bar squared. Okay, so unfortunately, this one is not as easy to solve as the phi portion that we just completed. Okay, so in order to solve this equation, it requires us to perform a change of variable trick. So you may have done this before in a previous math class. Okay, but all we're going to do here is say that x equals cosine theta, and theta of theta equals p of x. Okay, so a couple of things to keep in mind here is that the limits on theta go from 0 to pi, okay, which means that the limits on our new x variable after our change of variable are going to be from -1 to 1. Okay, so x here is not our Cartesian coordinate. Okay, it's just a new variable that we're using. So just be careful on that. So don't confuse that with our Cartesian coordinate x. Okay, so we're just changing our variable here. We're going from theta to a variable of x. Okay, so once you perform that change of variable, you can derive the following equation here from our equation that we started with up here. Okay, so if you are up for a challenge, you can feel free to take a minute and see if you can actually do that derivation with the change of variable. But basically, we're just going from this form of our equation to this, and that we did that using the substitution here, our change of variable. Okay, so this expression here has a special name. This is called Legendre's equation. Again, something that pops up frequently in math and physics. Okay, so this is not unique to our purposes. Okay, but it's going to be part of our solution to our theta component of our wave functions. Okay, so you'll see this equation come up a lot when you're working in spherical coordinates. Okay, so the downside of Legendre's equation is that it involves using something called the power series method. We're not going to take the time to do that because this is where we draw the line between being a chemistry class and a math class. Okay, so again, you're welcome to tackle that experience if you're so inclined. Okay, Macquarie, I think, walks through it, and you can also find that in a number of math texts, okay, walking through that method. But we're just going to go straight to the fun stuff. So it turns out when you solve Legendre's equation, in order for our solutions to be finite at our limits at x equals plus or minus 1, for our limits on the x, we have to truncate our series, and we end up with beta being equal to j times j plus 1. Okay, and then using our relationship here, again, remember we're always interested in the energy, so we'll just rearrange that expression to solve for energy. That gives us energy levels as such. So this expression may look familiar from our discussion on the energy levels for the rigid rotor that we sometimes just skip to. Okay, so these are the energy levels, the expression for the energy levels for the rigid rotor system. Again, just a reminder, the way we ended up here is that we have the requirement that our solutions have to be finite at our limits of x plus or minus 1. Okay? Now, the solutions to Legendre's equation when m is equal to 0 have a special name. They are called the Legendre polynomials, okay, and they're denoted with the notation p sub j of x, okay? So this notation that you're seeing here, or over here actually, more explicitly, these numbers in the subscript, right, are just denoting your energy level, your J. Okay, so this side has the Legendre polynomials in terms of our x variable, okay, which is what we have been working with most recently, but you can also put those in terms of our original theta variable, so we can convert those back into our cosine theta version. So just remember that change of variable over here. Okay, so you'll see tables of the Legendre polynomials either in x or in the cosine theta form. Either one is perfectly fine to use. It just depends on what your situation is. Okay, so normally you can just look these up in a table when you need them, but if for some reason you would need to put them together on your own, or it's kind of nice just to see where these are coming from, this is the generating formula for the Legendre polynomials. Okay, so here again, J is just our energy level, and then one other note I just want to make here is that, again, the notation for that index, that energy level, historically for spectroscopy, we use J to indicate the energy level. You may also sometimes see the lowercase l used to denote that. We're actually going to move into using the L notation in our next section when we talk about the hydrogen atom and angular momentum. Okay, those traditionally use the L version, but for when we're talking about rigid rotor and rotational spectroscopy, they like to stick with the J, and that's just kind of a historical convention. I will have a tendency to slip into L when I'm working with these because that's what I have worked with in my past, but you'll see both of them used. So just don't let that confuse you. These are essentially interchangeable and represent the same thing. Okay, so our generating formula here we can see leads to polynomials in X, and those polynomials will be even or odd depending on whether your J is even or odd. So we'll get an even function if J is even, okay, as we see for these, or we'll get an odd function if J is odd, okay, as we see with these. All right, so now we want to look at the other situation where m is not equal to 0. So in that case, the solutions to Legendre's equation are going to be given by what we call associated Legendre functions. Okay, so before we had Legendre polynomials, these are associated Legendre functions, and they are given the notation of p sub j to the absolute value of m. Okay, so here we see that we get that additional dependence on not only our energy level, our J quantum number, but we also get an additional dependence on our M quantum number. Okay, so once again, you can just generally look these up in a table. But if you wanted to put them together from scratch, you would use this generating formula, and we can see that they're defined in terms of the Legendre polynomials we just looked at previously. One thing to note here is that only the absolute value of m is relevant in our expression for the associated Legendre functions, and that is due to the fact that if we were to look back at our Legendre equation that we started with, it's only dependent on the square of m. Okay, so we only have to worry about the absolute value of m in our associated Legendre functions. Okay, so one thing that we want to remember is that it's theta and not x that is our variable of physical interest here. Okay, remember we're in our spherical coordinates, we're interested in the theta. Okay, so even though we did that change of variable to get to our solutions, okay, and you're going to find tables of your associated Legendre functions and Legendre polynomials in terms of x or cosine theta versions. Okay, it's really the theta versions that you're going to be wanting to use in when you're working with these. Okay, so now we're just going to take a minute to do a little just aside that helps us to rationalize how our energy levels for a rigid rotor are 2J plus 1 degenerate. Okay, so we'll see that come into play for us as we go along. And I'll just draw your attention to the fact that this is a proof in quotation, so we're just kind of using some logistical explanations here to get at that 2J plus 1 degeneracy. So the first thing we will look at is the fact that the defining equation of our Legendre polynomial tells us that J must be limited to non-negative integer values. So the limits on J, which I think we maybe forgot to mention earlier, our limits on J are integers starting at 0. So 0, 1, 2, and then so on from there. Then if we look at the defining equation of our associated Legendre functions, those tell us that if the absolute value of m is greater than j, then these functions are going to equal 0. So that is not a very interesting situation for us. So we then have the limit that the absolute value of m cannot be greater than our j value. Okay, so what that means is that for any given j, there are going to be 2j plus 1 values of m. Okay, so again, our limits on j will be integers starting at 0. Okay, and remember our m can take on positive and negative values as well as 0. So for any j that we have our possible m values, remember because we're looking at the absolute value, we can have both negative and positive values, including our 0. So that's what gives us that 2j plus 1 value. All right, so then since our energy levels depend only on the j, then our rigid rotor energy levels end up also being 2j plus 1 degenerate. Okay, so that's where that degeneracy comes from. So it all comes from all of these sort of caveats that come along with solving our theta part of the spherical harmonic wave functions. Okay, so now we're going to normalize the Legendre functions. So we'll just use the general form of our Legendre function, that p sub l to the absolute value of m, and we know that they are functions of cosine theta. Okay, so that's going to be our general form of our Legendre function. And then for normalizing, Okay, remember our limits on theta are 0 to pi. Okay, so you want to be careful to use the correct limits. And we'll put our function in here. And complex conjugate. But we see that these are not complex functions, so that's not really going to be significant for us in this context. The other thing to look out for is your differential volume element. It's a little bit different for this one than we have worked with before. Usually we've just had, dx or dy or d phi even in our spherical harmonics. The differential volume element for theta is a little bit different. This is going to be d theta sine theta. Okay, so just be careful with that. So I'll just make a little note here. That's your differential volume element for theta. Okay, and the other thing that we need to put in here is, since we're looking to normalize these, we know we're going to have a normalization constant. I'm just going to bring that out front. So we have an n squared, and we also know that we're going to have a function of L and M. Okay, so we'll just denote that with those indices in the subscript. Okay, so this is our kind of full setup of our normalization condition. So we know that we're going to want to have equal to 1 in order to determine our normalization constant. Just a quick note here that sometimes when you're looking at different texts, so from a Corey example, a lot of times you'll see that the differential volume element gets put out front. So this would start off with d theta sine theta p sub L to the absolute value of m, and so on. Okay, so you'll see this either tagged on at the end like I've done it here. So this is my habit for my differential volume elements from when I went through calculus. So that's my default, is to tag it on at the end, but a lot of times you'll see it put out front there. Either way's correct. Sometimes it's just a little bit of a way to simplify once you start doing multiple integrals. Okay, you just get everything out front. So you'll see that notation pop up once in a while. And just to zero in on our normalization constant, once you go through and solve this integral, you'll find that your normalization constant comes out to be this term right here. And I have just noticed that I have already slipped back into my L habit, which I warned I would do occasionally. So remember here, L and L equals J. Okay, so those are interchangeable. So I did slip back into my L habit. That's how I grew up developing these spherical harmonics. So I tend to go back into that pattern. But since we started this off with our spectroscopy application with the rigid rotor and our J notation, I'll just go back through and switch all of those to J's. So all those L's will become J's. And I'll do this in real time so you can see where I'm putting them in. So that will be of J and M, P sub J, and we want 2J plus 1 there, and then j minus the absolute value of m, and then j plus m, and one more right here. Okay, j and m. Okay, so now you've seen it in both versions with L's or M's. Again, they're equivalent, so please don't let this confuse you too much. Okay, it's just, like I said, conventional notation where J's are used when we're talking about the rigid rotor in spectroscopy, and for the rigid rotor, and then L's we're going to move into when we start moving into angular momentum in the hydrogen atom. Okay, they represent exactly the same thing. And if we put everything together that we've done between our phi and our theta components of the harmonic, spherical harmonic wave functions, we end up with this full equation here, where we have our spherical harmonic notation, where we see that y is a function of theta and phi, okay, and it depends on quantum numbers j and m. Okay, sometimes you'll see this written in a slightly different notation. Okay, so I'll just make a little note here. So sometimes you'll see it as just both indices on the bottom. Okay, they're the same thing. So don't let that notation confuse you. And then we have our normalization constant from the Legendre functions that we just looked at above. We have the Legendre function term here. Those are our functions of theta. Okay, and then we're just tacking on the wave function that we had from the phi component of solving our Schrodinger equation from before. Okay, and then you'll notice that our normalization constant is ever so slightly different. So we have this 4 pi term here instead of the 2 that we just derived up here. Okay, and that's just coming from the normalization constant that was in front of our e to the im phi from our phi component of the spherical harmonics. Okay, so remember that was 1 over the square root of 2 pi. Okay, so we're just bringing that in here. Okay, so this is the full expression of the rigid rotor wave functions. So make a note there. Okay, these are the spherical harmonics, the full expression. Okay, so we got there really just by solving our Schrodinger equation. Okay, so same approach as we've used before. Okay, just using some different Hamiltonian, different solutions there. Okay, so same process as before, separation of variables. Okay, there was a few steps that we skipped in terms of our power series method for the theta component of those wave functions, but again, you're welcome to go back if you feel comfortable and work through that if you like to see the full derivation of the theta component of the wave functions. But this is what we're going to work with when we're solving problems with our rigid rotor. Okay, so these are the wave functions that you're going to want to use.